Okay, so let's start from the beginning. So we, in chapter 7, we did confidence intervals. In chapter 8, we will do hypothesis testing. So hypothesis testing, we will learn the basics in 8.1. 8.2, we'll do a testing claim about a proportion. 8.3, we'll test a hypothesis about a mean. And then on the 8.4, we'll do the testing about the standard deviation. Okay, same thing that we did in chapter 7. Okay, hypothesis testing. Hypothesis testing is basically we go back to our basketball guy. Remember our basketball guy? The guy who said he was a 90% free throw shooter who couldn't shoot for crap, and then we kind of say, okay, we slammed him and said, well, statistically speaking, right? We did the testing and said, well, okay, you're not. Okay, so this is what we're going to do. So it's basically the same thing. So hypothesis testing. In hypothesis testing, you have two different hypotheses. Okay, so I have the null hypothesis, and then I have the alternative hypothesis. The ho and the ha. Okay, so the ho is the null hypothesis. And this is the alternative hypothesis. Okay? So, the alternative hypothesis is what we think is true. This is what we are trying to disprove. Right? So we are trying to disprove this, and we think this is true, okay? So in the basketball analogy, we think that the guy is full of crap and he's not a 90% free throw shooter, right? So we're trying to disprove the fact that he is a 90% free throw shooter, okay? So my null hypothesis would be, okay, this guy who showed up in my gym is a 90% free throw shooter, okay? My alternative hypothesis is that he is actually a less than 90% free throw shooter. Okay, so I'm trying to disprove that. Okay? So, we will find, so if you go to page 359, it shows you the definitions. Let's go and read that carefully. Okay? The null hypothesis, denoted by the ho, is a statement that the value of a population parameter, such as a proportion, mean, or standard deviation, is equal to some claimed value. Okay, the alternative hypothesis is the ha, the statement that the parameter has a value that is somehow differs from the hypothesis. Okay, so we can say that he is less than 90% free throw shooter, or we can just say that he is not a 90% free throw shooter, or it could be alternatively, he could be a greater than 90% free throw shooter. Okay, so that all depends on how we set it up. Okay, all right. Flip the page. There's this unwieldy long flow chart here. Okay, so basically we're gonna do the ho and the ha. We find that we set that up, and then when we do significance testing, just as we did with the confidence interval, what do we have to make sure? We had to make sure that there were three different assumptions, right? Right? What were the three assumptions? Simple random sample. 10%. Less than 10%. Large counts, right? Large counts for, what was the large counts requirement for proportion?
35. No.
30.
Okay, 30 if it's a mean, not for proportion. No, in proportion, the expected values NP or NQ had to be greater than 5, right? Okay, so that was our large count. So there are three different things, right? In significance testing, for each one we're going to use the exact same conditions. We're going to check for the exact same two conditions. Okay? All right? So the condition we're going to check for is it less than 10%? I mean, are we sampling less than 10%? Is it a random sample? And the large counts. Okay, so we're gonna check that, and then as long as we check that, we're gonna end up finding what is a p-value. We're gonna use our calculator, and we're gonna find a p-value, and we're gonna compare that against alpha. What was our alpha? Alpha was our significance level, right? Our significance, 95%, 90%, all that stuff. And if I didn't tell you what the significance level is, what are you are to assume? 5% or 95%, right? 95% significance level, otherwise known as the alpha of 5%, right? Because this is basically 1 minus the significance, 1 minus the significance level. Okay, all right. So that's how we'll do it. If the p-value is less than the alpha, that's what we want to find. We want to come to a conclusion that this happens. We want to say that the p-value is less than 5%. P-value means that what is the probability of the things that we found, right? He shot like 32 out of 50, I think, or something like that, whatever. What is the chances of this happening if he was a 90% free throw shooter? Okay? And if we find that p-value to be less than 5%, we can say that, well, this is statistically significant or not. It's significant, right? He is so bad. This is so bad that there is no way, or there is less than 5% chance that this happens because he's having a bad day, right? And therefore, we will reject the hoe. We will reject the hoe, meaning he is a 90% free throw shooter. We have significant evidence that actually he has less than 90% free throw shooter. We have significant evidence for the alternative hypothesis. Okay? The thing to remember this is that if for some reason we find this happen, what does that mean? That means that the probability of this happening by sheer chance is greater than our significance level. So there's actually a probability, a good probability, that's not significant enough. So at that point, we do not accept the hoe. You never, ever accept the hoe. Right? You either reject it or you fail to reject. Okay? And this is significant because you have to, when you write your conclusion, you will always write we either reject or we fail to reject. Okay? So, if the p-value is larger, fail to reject. If the alpha is bigger, we reject. Okay, so let's look at the flowchart now. Now that I kind of explained to you, see if this flowchart makes sense. Okay? 1, identify the claim. 2, give it, okay, so we're going to write that in p hat is equal to something or whatever or whatnot or whatever, right? 3, identify the null and alternative hypothesis. You set the hoe and the ha up. 4, select a significance level. Okay, again, the alpha, this is the setting of the alpha values. Okay, and then you identify the test statistic, whether you're going to use a normal or a t distribution or a chi-square. Okay, so, and then, so you would find we're going to do the p-value method here. Okay. Find the value of the test statistic and the p-value. Once you find the p-value, 7, make a decision. Reject the hoe if alpha is greater than p-value. And that's what we want, right? We want the alpha to be bigger than the p-value. Okay, so we're looking for a smaller p-value most of the times. Okay? or we fail to reject if the p-value is larger than the alpha, okay? And then at the 8, restate the decision in a non-technical, in other words, this is where we conclude, all right? We conclude in this part, in this one example, we conclude that we reject the hypothesis that the player is a 90% free throw shooter. We have significant evidence that he is actually a less than 90% free throw shooter. Okay, so you have to write this down. In other words, you have to write this, conclude this within the context of the question. Does that make sense? You just can't say at the end. So this is a typical mistake that you guys make. Oh, p-value, so the alpha value is greater than p. We reject the ho. I have significant evidence for the ha. I don't want to know that. I want to know what you're actually trying to tell me. I want to know what you actually concluded, right, within the context of the problem. Okay, because that shows me full understanding of what you were doing. Okay? That's that. And then there's that pink thing. Okay, so let's not worry about the pink thing right now. We'll just do the green thing right now. Okay. So, on page 361, it says, select the significance level alpha. Okay. Significance level alpha for a hypothesis test is probability. Okay, here we go. It is the probability value used as the cutoff for determining when the sample evidence constitutes a significant evidence. So the smaller the alpha value is, what does that mean? That means that so it's a 99% free throw, 99% significance level, or a 99.5, right? If I go that far, I'm actually making the p-value less and less likely to be less than the alpha value, right? So I'm giving more and more benefit of the doubt. Does that make sense? Right, you see that? You see how that logic flows there? Okay. Flip the page. There's a table 8.2. I want you to read that. Just kind of glance over it. And see if these things ring a bell for you. Does that all ring a bell? It should ring a bell. It's all the stuff you've done, right? When you did the confidence intervals, remember? We did the confidence intervals, right? We did the confidence interval. We said that proportion is always going to be normal. We actually found the z critical alpha divided by 2 and that stuff. Remember that? Okay, so that wasn't the proportion, right? And we were doing the mean. It was the t, right? Using the degree of freedom and all that stuff. We did the t interval test, right? Okay, or we could sometimes do the normal test, all right? So when we do that, if sigma is known, okay, but then again, it's very, very rare that the sigma is going to be known. So more than likely, you will be using the t star rather than the z star there. And then the chi-square is what we did for the sigma, what we did for the standard deviation. This is all stuff we did. Okay, so it's basically should have been a review there. And we will stop right here. Let's stop right here. I don't want to bite off too much today.